Hi, everyone, and welcome back for part two of chi-square test of independence. All we're doing in this quick video is going over the second practice problem from the lecture. So if you haven't done this problem yet, I want you to stop and try and solve this problem right now before watching the video. Test yourself, see if you can do it. And then after you've given it a shot, come back and watch this video, and I will walk you through it. There we go. So if you haven't done the problem yet, press pause. If you have done the problem, then let's dive into the answers. So the question before us is profession independent of whether you rent or own a home, right? So we're asking, does your profession, whether you're a doctor, a lawyer, or a teacher, have any impact on your status in this other variable, right? Whether you rent or own a home. So are these two variables, profession and home ownership, are they independent of each other or not? Right? That's what this test of independence is asking. Use the data below from 600 people and assume alpha equals 0.01 to answer the question. So remember back to our steps from the first part of this lecture. The very first thing we have to do is total every row and every column. So we're just going to add up all the numbers in rent and put our total here, add up all the numbers in own, put it here, add up all the teachers, all the lawyers, all the doctors, so on and so forth. So once we just do all of our sums, we end up with this. We actually have an equal number of renters and owners. That doesn't have to be the case. It's just how the data worked out. And then you can see that we do have an unequal number of people in different professions. That's okay. You can't control what profession people have. And so that's just the way the data worked out. No problems there. These do not have to be even. So now that we have our row and our column totals, we're going to use those row and column totals to derive our expected values. Remember, keep in mind that all of these numbers here in the matrix of this chart, right, the 75, 115, 110, 105, 105, and 90, that's all observed data. That's real data. That's what we observed in the world. These numbers represent actual real people and where they fall in these categories. So we have the O's. We have the observed data. What we need are our E's. We need our expected values so that we can compare the observation to the expectation. So we derive our expected values for each cell. We're going to have 6 because we need one expected value for each of our data cells. We simply use this little formula, row total times column total divided by n, where n equals the total number of participants. Remember, n is going to be 600 because we had 600 participants that was specified in the question. So we're going to take for each cell, so for example, doctors who rent, the column total was 165. The row total was 300. So we just do 165 times 300 divided by 600 for our total number of participants. So you select a cell that you're going to work on, then you take its column total for that cell, and then the row total for that cell, and you multiply them together. And then you divide by n. So you can see here that's been done for each of our data cells. Go ahead and check your answers. Okay, now that we have our expected values, we have everything we need. We have the observations, and we have the O's, we have the E's. Now we just plug and chug into this formula, right? That's all we're going to do. So we're going to have to do this right side of the formula 6 times, right? 1 for each of our real data cells. So we're going to do the right side of the formula for doctors who rent. We're going to do the right side of the formula for doctors who own. We're going to do the right side of the formula for lawyers who rent and lawyers who own, right? So on and so forth. We're going to get a chi-square contribution, so to speak. We're going to get a number, right, is going to pop out for every single cell. So we're going to end up with 3 numbers per cell. We have the observations, the real data. We have the expected value, our E's up here. Turn on my laser pointer. And then we'll end up with a chi-square contribution for each cell. We will have 6 of them. So all we're going to do is we take the observed value, for example, 75 is our O for Dr. Rent. 75 minus 82.5. Then we square that value, and then we divide again by 82.5, right, the expected value. We just do that for each cell. And here's what you look like, right? We can see if you do the math, right, this is your value for Dr. Rent, 0.68. Here's your value for lawyer rent. Here's your value for teacher rent, doctor own, lawyer own, teacher own. So go ahead and check your answers, right? Again, I derived these values simply by doing the right side of this formula once for each of my cells. So 75 minus 82.5 squared divided by 82.5 is 0.68. 115 minus 110 squared divided by 110 is 0.23. So we have all these numbers. We add them all up, and we get 1.94. Forgive that errant period right there. We end up with 1.94 as our final chi-square after we sum all of these values, right? We did the right half 6 times, and now we have to sum them all up. So we need to find our critical chi-square value. If you remember back to the problem, alpha was 0.01. We derived degrees of freedom using this formula, the number of rows minus 1 times the number of columns minus 1. So there were 2 rows, right, rent and own, and there were 3 columns, teacher, lawyer, doctor, right? So 2 minus 1 is 1, 3 minus 1 is 2, so 1 times 2 equals 2. So with an alpha of 0.01 and 2 degrees of freedom, we have a chi-square critical value of 9.210. That is our benchmark. That's our hurdle. If our calculated chi-square is greater than that value, then we reject the null and we conclude that the 2 variables are not independent, right? They are impacting each other. If our chi-square is less than the critical value, then we fail to reject the null and we conclude that the 2 variables are independent, meaning they are not having an impact on each other. So 9.210, we simply compare that to our computed chi-square, which was 1.94. We didn't even come close here, right? Nothing's going on. There is no statistical significance. Remember, our null and our research hypotheses, the null would be that they are independent, because that would mean that nothing is going on, right? They're not impacting each other, right? If they're independent, then there's nothing going on. Right? So that's our null hypothesis. Our research is that they are not independent. Well, we did not clear our hurdle. We are much lower than our hurdle, which means that we held on to the null and we're going to keep it. We are going to fail to reject the null. So we are going to conclude, in fact, that profession and home ownership are independent of one another, meaning it doesn't matter what kind of job you have. People own and rent the same sort of frequency, basically. Home ownership is not impacted by profession in these data. So we set up the null, right, which was nothing is going on. We held on to the null, and we were not convinced, right? This is not a convincing result. It's less than our hurdle. It's less than our line in the sand. And so we fail to reject the null. We continue to hold on to that null hypothesis. And here's what your APA-style conclusion should look like. A chi-square test of independence was conducted to determine whether profession and home ownership are independent. So that's introducing our test and then introducing our research question. We fail to reject the null, and we're going to conclude profession and home ownership are independent. Chi-square, 2 degrees of freedom, 600 participants equals 1.94, not significant. Thus, profession does not impact whether or not a person owns a home or rents. So profession has no impact on home ownership. Okay. We actually have, sorry, I forgot about this at the beginning of the lecture. We have just a couple more slides because what we're going to, oh, sorry, yes, you have practice problems and answers on iCollege. Make sure you take a look at those. It's going to be very important to make sure you get enough practice. We have just a few slides, I think just like 6 or 7 slides on central tendency. This should be pretty straightforward. You have encountered central tendency many, many times in your life before. We're just going to talk a little bit about the different types of central tendency and when or why some might be better than others. So, central tendency describes the typical score of a set of data. Right? That's what we want to do when we have a measure of central tendency. We want a single score that best describes the entire data. Typically, what that is the mean or the average, right? That's when something is the average, what that means is that it's the most typical score from that data set, or it is best at describing the most typical score in that data set. So the mean is just, the average. You can also use median, which we'll talk about, and then mode, which is the most frequent score. So in statistics, we are by and large only going to deal with averages. When we do calculations, the average is just the thing we need. Arithmetically and mathematically, that's the most important measure of central tendency. So we won't really work with median or mode, but we do want to understand some of the limitations of the mean. And that's really what we're going to focus on here. So it looks big and scary, but this is the actual arithmetic formula for a mean. So you take, right, each value, each x, starting with the first one, and then you add them all up, right? You sum however many there are, and then you divide by how many there are, right? That's how you do an average. You sum all your scores and you divide by how many scores there are. So for example, if we had these data on the number of Facebook friends that someone has, right? We have 11 Facebook users. This each of these numbers represents the number of friends that a Facebook user has. We add them all up, we get 1,045 divided by 11 data points, right? People gives us an average of 95 Facebook friends. We like the mean and we want to use it above all other measurements of central tendency. In particular, when we have a nice, even symmetric distribution, meaning that the data are just nice and smooth and there's lots of data around the mean, right? That's the most, that's where the data aggregates, right? Most people are average, right? If we're looking at, for example, IQ, IQ of 100 is the average IQ, and most people are right around 100. Right? That's what this height means, right? There's a lot of data right here. And then as we get more extreme, meaning as we get, let's just continue using IQ, as we get lower and lower and lower in IQ, there are fewer and fewer people out in that area of the distribution, meaning there's lots of people that have an IQ of 100, that's the mean. There are not a lot of people that have an IQ of 75 or 65. It's less common. Right? That's what the height of this graph means. And the same thing going above the mean, right? There are lots of people with an IQ of 100. There's not a lot of people with an IQ of 130. That's really, really high. Now, in a symmetric distribution, the mean, the median, and the mode are all the same value. So the average is also the midpoint of the data, right? That's what the median means. And it's also the most frequent score in the data set. But as distributions or as data sets become non-symmetric, or as they become skewed, if we remember that from a while ago, as a distribution of data becomes skewed, then some funny things start to happen to the mean. The mean can be negatively impacted by that distribution, as we'll see in a second. So quickly, the mode is just the most frequent score, right? Which score occurs the greatest number of times. Data sets can have multiple modes. So you can have a bimodal distribution, which is what this one on the left looks like. I want you to imagine that these are exam scores, such that on the right are good scores and on the left are bad scores. In the middle, right, are people who get C's. So a bimodal distribution on like an exam would indicate that you either really understood the material, right? Lots of people got A's and lots of people got F's and very few people got C's. So basically you either knew it or you didn't know it, right? It's bimodal. There's almost two categories that people are falling into, and then they're washing out of the middle. And of course, you can have one mode, you can have two modes, you could be multimodal, right? This is just sort of an indicator of the frequency of certain scores and certain scores being more common than others, right? That's the mode. What is the most frequent score? The median is the middlemost score. So if we take our Facebook friend user data and we order it starting with the lowest number on the left and sequentially with the highest number on the right, we find the middle point, right? And that's our median. So our median is 98. This will happen when you have an odd number of data points, right? We had 11, so we have a midpoint. If you have an even number of data points, then there is no midpoint to the data. And so you take the two most middle pieces of data and you average them. That's what you do to find the median when you have an even number of data points. And there is no actual like direct middle score. So let's talk about skewness. When a distribution is skewed, like this one, here we have a positive skew. These extreme data points over here pull the mean towards it more so than they pull the median or the mode. So these data points are what we call outliers. And they can, in extreme cases, make the mean not the best descriptor of the data. So in a data set with extreme outliers, we may not want to use the mean as a descriptor. We might want to use the median because the median is more resilient. It's not impacted by extreme variations as much. So a silly example, and then we'll see a serious example. So a silly example might be if I collected data from this class on the number of, NBA All-Star games that you have played in. Raise your hand if you've played in an NBA All-Star game. No, none of you have. 0, right? Everyone would get a 0. 0, 0, 0, 0, 0, 0, 0, 0. Our average is 0, and that's good because it perfectly describes the data. But what if, for some reason, Michael Jordan was taking this class? Suddenly, it's 0, 0, 0, 0, 0, 0, and then 18 or 15, however many NBA All-Star games he's played in. So suddenly, he is an extreme outlier, and he is going to change our average, right? Maybe just because of the addition of him, then the average number of NBA All-Star games that the class has played in becomes like 1 or 1.5. And that's not a good description because it doesn't actually describe the reality of our class. It just describes Michael Jordan, right? Just this one extreme value is pulling the mean towards it, and the mean is no longer representative of the full set of data. And so in that case, we might want to use the median to describe the data, although we will always use the mean when doing statistics. Another place where you often see the median used is in economics for describing income. In this chart, we see data from 2010 from the U.S. Census in 2010, and it's basically a frequency diagram. They've done percentages on the y-axis. So the height of the bar represents the percentage of households in the United States that make this amount of money, starting at under 5,000 and going up in increments of 5,000. And then here on the high end, you start to get some, you get a bigger jump over here. So basically, if you're over here on the left, you make very little money. If you're over here on the right, you make a lot of money. When we describe household income in the United States, we use the median because the median is more representative of the country as a whole than the average. Why? Because these insanely wealthy people are pulling the average towards them, right? I mean, how much money do like Bill Gates, Elon Musk, Jeff Bezos, those people, like they're worth billions and tens of billions of dollars, right? They make, tens of millions of dollars a year. And there's a good number of people out there, something like 4% of households report an income of over $200,000, but they are not representative of the population. But because they have these extreme high values, just like Michael Jordan, right, with NBA All-Star games, they pull the average household income with them, right? They impact the mean, but they impact the median less. And so when we're talking about like national level economics, you will usually hear people discuss income in terms of the median, not in terms of the mean. Okay. That's it. That's a quick little foray into central tendency. Thanks for watching, and I will see you next time. Have a good one.